Eiffel is an ISO standardized, object-oriented programming language designed by Bertrand Meyer and Eiffel Software. The design of the language is closely connected with the Eiffel programming method. Both are based on a set of principles, including design by contract, command query separation, the uniform access principle, the single choice principle, the open-closed principle, and option-operand separation. Many concepts initially introduced by Eiffel later found their way into Java, C, and other languages. New language design ideas, particularly through the Ecma ISO standardization process, continue to be incorporated into the Eiffel language. Characteristics. The key characteristics of the Eiffel language include an object-oriented program structure in which a class serves as the basic unit of decomposition. Design by contract tightly integrated with other language constructs. Automatic memory management, typically implemented by garbage collection. Inheritance, including multiple inheritance, renaming, redefinition, select, non-conforming inheritance, and other mechanisms intended to make inheritance safe. Constrained and unconstrained generic programming, a uniform type system handling both value and reference semantics in which all types, including basic types such as integer, are class-based. Static typing, void safety, or static protection against calls on null references, through the attach types mechanism. Agents, or objects that wrap computations, closely connected with closures and lambda calculus. Routines, or routines evaluated only once, for object sharing and decentralized initialization. Keyword-based syntax in the ALGOL Pascal tradition but separator-free, insofar as semicolons are optional, with operator syntax available for routines. Case insensitivity, simple concurrent object-oriented programming facilitates creation of multiple, concurrently active execution vehicles at a level of abstraction above the specific details of these vehicles. Design goals. Eiffel emphasizes declarative statements over procedural code and attempts to eliminate the need for bookkeeping instructions. Eiffel shuns coding tricks or coding techniques intended as optimization hints to the compiler. The aim is not only to make the code more readable, but also to allow programmers to concentrate on the important aspects of a program without getting bogged down in implementation details. Eiffel's simplicity is intended to promote simple, extensible, reusable, and reliable answers to computing problems. Compilers for computer programs written in Eiffel provide extensive optimization techniques, such as automatic inlining, that relieve the programmer of part of the optimization burden. Background. Eiffel was originally developed by Eiffel Software, a company founded by Bertrand Meyer. Object-oriented software construction contains a detailed treatment of the concepts and theory of the object technology that led to Eiffel's design. The design goal behind the Eiffel language, libraries, and programming methods is to enable programmers to create reliable, reusable software modules. Eiffel supports multiple inheritance, genericity, polymorphism, encapsulation, type-safe conversions, and parameter covariance. Eiffel's most important contribution to software engineering is design by contract, in which assertions, preconditions, postconditions, and class invariants are employed to help ensure program correctness without sacrificing efficiency. Eiffel's design is based on object-oriented programming theory, with only minor influence of other paradigms or concern for support of legacy code. Eiffel formally supports abstract data types. Under Eiffel's design, a software text should be able to reproduce its design documentation from the text itself, using a formalized implementation of the abstract data type. Implementations and environments. Eiffel Studio is an integrated development environment available under either an open source or a commercial license. It offers an object-oriented environment for software engineering. Eiffel Envision is a plugin for Microsoft Visual Studio that allows users to edit, compile, and debug Eiffel projects from within the Microsoft Visual Studio IDE. 5 other open-source implementations are available: the Eiffel compiler Tcomp, Gobo Eiffel, Smart Eiffel, the GNU implementation, based on an older version of the language Euro, Liberty Eiffel Euro based on the Smart Eiffel compiler Euro, and Visual Eiffel. Several other programming languages incorporate elements first introduced in Eiffel. Sather, for example, was originally based on Eiffel but has since diverged, and now includes several functional programming features. The interactive teaching language Blue, forerunner of BlueJ, is also Eiffel-based. The Apple Media tool includes an Eiffel-based Apple Media language. Specifications and standards The Eiffel language definition is an international standard of the ISO. The standard was developed by Ecma International, which first approved the standard on June 21, 2005 as Standard Ecma 367, Eiffel, Analysis, Design and Programming Language. In June 2006, Ecma and ISO adopted the second version. In November 2006, ISO first published that version. The standard can be found and used free of charge on the Ecma site. The ISO version is identical in all respects except formatting. Eiffel software, the Eiffel compiler Tcomp and Eiffel library developer Gobo have committed to implementing the standard. Eiffel Software's Eiffel Studio 6.1 and the Eiffel compiler Tcomp implement some of the major new mechanisms Euro in particular, inline agents, assigner commands, bracket notation, non-conforming inheritance, and attach types. The Smart Eiffel team has turned away from this standard to create its own version of the language, which they believe to be closer to the original style of Eiffel. Object Tools has not disclosed whether future versions of its Eiffel compiler will comply with the standard. Liberty Eiffel implements a dialect somewhere in between the Smart Eiffel language and the standard. The standard cites the following: predecessor Eiffel language specifications, Bertrand Meyer, Eiffel the language, Prentice Hall, second printing, 1992, Bertrand Meyer, Standard Eiffel, ongoing, 1997 Euro present, at Bertrand Meyer's ETL3 page, and Bertrand Meyer, Object-Oriented Software Construction, Prentice Hall, first edition, 1988. Second edition, 1997. Bertrand Meyer, Touch of Class, Learning to Program Well with Objects and Contracts, Springer Verlag, 2009 ISBN 978-3-540-92144-8 LXIV plus 876 pages full color printing, numerous color photographs. The current version of the standard from June 2006 contains some inconsistencies. The Ecma committee has not yet announced any timeline and direction on how to resolve the inconsistencies. Syntax and semantics. Overall structure an Eiffel system, or program is a collection of classes. Above the level of classes, Eiffel defines cluster, which is essentially a group of classes, and possibly of subclusters. Clusters are not a syntactic language construct, but rather a standard organizational convention. Typically an Eiffel program will be organized with each class in a separate file, and each cluster in a directory containing class files. In this organization, subclusters are subdirectories. For example, under standard organizational encasing conventions, XE might be the name of a file that defines a class called X. A class contains features, which are similar to routines, members, attributes, or methods in other object-oriented programming languages. A class also defines its invariants, and contains other properties, such as a notes section for documentation and metadata. Eiffel standard data types, such as integer, string and array, are all themselves classes. Every system must have a class designated as root, with one of its creation procedures designated as root procedure. Executing a system consists of creating an instance of the root class and executing its root procedure. Generally, doing so creates new objects, calls new features, and so on. Eiffel has 5 basic executable instructions: assignment, object creation, routine call, condition, and iteration. Eiffel's control structures are strict in enforcing structured programming. Every block has exactly one entry and exactly one exit. Scoping, unlike many object-oriented languages, but like Smalltalk, Eiffel does not permit any assignment into fields of objects, except within the features of an object, which is the practical application of the principle of information hiding or data abstraction, requiring formal interfaces for data mutation. To put it in the language of other object-oriented programming languages, all Eiffel fields are private, and setters are needed to modify values. An upshot of this is that setters can, and normally do, implement the invariants for which Eiffel provides syntax. While Eiffel does not allow direct access to the features of a class by a client of the class, it does allow for the definition of an assigner command, such as SUMAttribute, SUMType assign set SUMAttribute. Set SUMAttribute, set value of SUMAttribute to v. Do, SUMAttribute, equals v, end. While a slight bow to the overall developer community to allow something looking like direct access, the practice is dangerous as it hides or obfuscates the reality of a setter being used. In practice, it is better to read the direct call to a setter rather than implying a direct access to a feature like SUMAttribute as in the example code above. Unlike other languages, having notions of public, private, and so on, Eiffel uses an exporting technology to more precisely control the scoping between client and supplier classes. Moreover, the export logic used can be checked statically by the compiler, which allows earlier detection of scope-violating calls at compile time rather than runtime. For example, the none is similar to private in other languages. Scope applied this way to a feature set can be changed in descendant classes using the export keyword. Alternatively, the lack of AX export declaration implies any and is similar to the public scoping of other languages. Finally, scoping can be selectively and precisely controlled to any class in the Eiffel project universe, such as here, the compiler will allow only the classes listed between the curly braces to access the features within the feature group. Hello, world. A programming language's look and feel is often conveyed using a hello, world program. Such a program written in Eiffel might be: this program contains the class Hello World. The constructor for the class, named Make, invokes the print system library routine to write a Hello World message to the output. Design by contract equals. The concept of design by contract is central to Eiffel. The contracts assert what must be true before a routine is executed and what must hold to be true after the routine finishes. Class invariant contracts define what assertions must hold true both before and after any feature of a class is accessed. Moreover, contracts codify into executable code developer and designers' assumptions about the operating environment of the features of a class or the class as a whole by means of the invariant. The Eiffel compiler is designed to include the feature and class contracts in various levels. Eiffel Studio, for example, executes all feature and class contracts during execution in the workbench mode. When an executable is created, the compiler is instructed by way of the project settings file to either include or exclude any set of contracts. Thus, an executable file can be compiled to either include or exclude any level of contract, thereby bringing along continuous levels of unit and integration testing. Moreover, contracts can be continually and methodically exercised by way of the auto-test feature found in Eiffel Studio. The design by contract mechanisms are tightly integrated with the language and guide redefinition of features in inheritance, routine precondition. The precondition may only be weakened by inheritance. Any call that meets the requirements of the ancestor meets those of the descendant. Routine postcondition. The postcondition can only be strengthened by inheritance. Any result guaranteed by the ancestor is still provided by the descendant. Class invariant. Conditions that must hold true both before and after access to a class feature. Because the invariant is checked so often, it makes it simultaneously the most expensive and most powerful form of condition or contract. In addition, the language supports a check instruction, and loop invariants. Void safety void safety, like static typing, is another facility for improving software quality. Void-safe software is protected from runtime errors caused by calls to void references, and therefore will be more reliable than software in which calls to void targets can occur. the analogy to static typing is a useful one. In fact, void-safe capability could be seen as an extension to the type system, or a step beyond static typing, because the mechanism for ensuring void safety is integrated into the type system. The guard against void target calls can be seen by way of the notion of attachment and detachment. The void-safe facility can be seen in a short rework of the example code used above. Some attribute, detachable some type. Use some attribute, set value of some attribute to v. Do, if attached some attribute is L attribute then, do something, end. Do something with a value. Do. Doing something with a value. End. The code example above shows how the compiler can statically address the reliability of whether some attribute will be attached or detached at the point it is used. Notably, the attached keyword allows for an attachment local, which is scoped to only the block of code enclosed by the if statement construct. Thus, within this small block of code, the local variable can be statically guaranteed to be non-void. Features, commands, and queries equals. The primary characteristic of a class is that it defines a set of features, as a class represents a set of runtime objects, or instances. A feature is an operation on these objects. There are two kinds of features, queries and commands. A query provides information about an instance. A command modifies an instance. The command-query distinction is important to the Eiffel method. In particular, uniform access principle, from the point of view of a software client making a call to a class feature, whether a query is an attribute or a function should not make any difference. For example, a vehicle speed could be an attribute accessed on the object a vehicle, or it could be computed by a function that divides distance by time. The notation is the same in both cases, so that it is easy to change the class's implementation without affecting client software. Command-query separation principle. Queries must not modify the instance. This is not a language rule but a methodological principle. So in good Eiffel style, one does not find get functions that change something and return a result. Instead there are commands to change objects, and queries to obtain information about the object, resulting from preceding changes. Overloading Eiffel does not allow argument overloading. Each feature name within a class always maps to a specific feature within the class. One name, within one class, means one thing. This design choice helps the readability of classes, by avoiding a cause of ambiguity about which routine will be invoked by a call. It also simplifies the language mechanism. In particular, this is what makes Eiffel's multiple inheritance mechanism possible. Names can, of course, be reused in different classes. For example, a feature class is defined in several classes, integer, real, string, etc. Genericity. A generic class is a class that varies by type. Classes can be generic, to express that they are parameterized by types. Generic parameters appear in square brackets. G is known as a formal generic parameter. With such a declaration, G represents within the class an arbitrary type. So a function can return a value of type G, and a routine can take an argument of that type. The list, integer and list, word are generic derivations of this class. Permitted combinations are integer and word are the actual generic parameters in these generic derivations. It is also possible to have constrained formal parameters, for which the actual parameter must inherit from a given class, the constraint. For example, in a derivation hash table, integer, string is valid only if string inherits from hashable. Within the class, having key constrained by hashable means that for x, key it is possible to apply to x all the features of hashable, as in x hashcode. Inheritance basics to inherit from one or more others, a class will include an inherit clause at the beginning. The class may redefine some or all of the inherited features. This must be explicitly announced at the beginning of the class through a redefined subclause of the inheritance clause, as in. See for a complete discussion of Eiffel inheritance. Deferred classes and features Classes may be defined with deferred class rather than with class to indicate that the class may not be directly instantiated. Non-instantiatable classes are called abstract classes in some other object-oriented programming languages. In Eiffel parlance, only an effective class can be instantiated. A feature can also be deferred by using the deferred keyword in place of a do clause. If a class has any deferred features, it must be declared as deferred. However, a class with no deferred features may nonetheless itself be deferred. Deferred classes play some of the same role as interfaces in languages such as Java, though many object-oriented programming theorists believe interfaces are themselves largely an answer to Java's lack of multiple inheritance. Renaming equals, a class that inherits from one or more others gets all its features, by default under their original names. It may, however, change their names through rename clauses. This is required in the case of multiple inheritance if there are name clashes between inherited features. Without renaming, the resulting class would violate the no-overloading principle noted above and hence would be invalid. Tuples types may be viewed as a simple form of class, providing only attributes and the corresponding setter procedure. A typical tuple type reads and could be used to describe a simple notion of birth record if a class is not needed. An instance of such a tuple is simply a sequence of values with the given types, given in brackets, such as. Components of such a tuple can be accessed as if the tuple tags were attributes of a class. For example, if T has been assigned the above tuple, then T weight has value 3.5. Thanks to the notion of assigner command, dot notation can also be used to assign components of such a tuple, as in. The tuple tags are optional, so that it is also possible to write a tuple type as tuple, string, real, date. The precise specification of, for example, tuple, a, b, c, is that it describes sequences of at least 3 elements, the first 3 being of types A, B, C respectively. As a result, tuple, a, b, c, conforms to tuple, a, b, to tuple, a, and to tuple, the topmost tuple type to which all tuple types conform. Agents Eiffel's agent mechanism wraps operations into objects. This mechanism can be used for iteration, event-driven programming, and other contexts in which it is useful to pass operations around the program structure. Other programming languages, especially ones that emphasize functional programming, allow a similar pattern using continuations, closures, or generators. Eiffel's agents emphasize the language's object-oriented paradigm, and use a syntax and semantics similar to code blocks in Smalltalk and Ruby. For example, to execute the myAction block for each element of my list, one would write. To execute myAction only on elements satisfying my condition, a limitation filter can be added. In these examples, myAction and myCondition are routines. Prefixing them with agent yields an object that represents the corresponding routine with all its properties, in particular the ability to be called with the appropriate arguments. So if the represents that object, the instruction will call the original routine with the argument x, as if we had directly called the original routine, myAction. Arguments to call are passed as a tuple, here, x. It is possible to keep some arguments to an agent open and make others closed. The open arguments are passed as arguments to call, they are provided at the time of agent use. The closed arguments are provided at the time of agent definition. For example, if action 2 has 2 arguments, the iteration iterates action 2 for successive values of x, where the second arguments remain set to y. The question mark indicates an open argument. Y is a closed argument of the agent. Note that the basic syntax agent f is a shorthand for agent f with all arguments open. It is also possible to make the target of an agent open through the notation T, where T is the type of the target. The distinction between open and closed operands corresponds to the distinction between bound and free variables in lambda calculus. An agent expression such as action 2 with some operands closed and some open corresponds to a version of the original operation carried on the closed operands. The agent mechanism also allows defining an agent without reference to an existing routine, through inline agents as in. The inline agent passed here can have all the trappings of a normal routine, including precondition, postcondition, rescue clause, and a full signature. This avoids defining routines when all that's needed is a computation to be wrapped in an agent. This is useful in particular for contracts, as in an invariant clause that expresses that all elements of a list are positive. The current agent mechanism leaves a possibility of runtime type error if a routine with n arguments is passed to an agent expecting m arguments with m.